Previously, we have talked about the different operations on matrices. We had matrix addition, scalar multiplication, and matrix multiplication. Now we're going to look into another helpful property of a matrix for its operations, the inverse of a matrix. So we have in real numbers what we call the multiplicative inverse. So we're given an equation here, ax equals b, wherein a and b are real numbers and a is not equal to 0. If we would like to solve for the variable x, what we would usually do is divide both sides by a. Therefore, x will be equal to b over a. Now, remember that this division, apart from that, another way of telling it would be this one. We multiply both sides of the equation by 1 over a, which will give us the same result. This 1 over a in real numbers is what we call the multiplicative inverse of the real number a. So that would mean that if you multiply a real number to its multiplicative inverse, as you can see here, it gets cancelled out, which gives us 1, which is our multiplicative identity. Same is true for matrices. So this is the definition of the inverse of a matrix. An n by n matrix A is invertible or non-singular where there exists an n by n matrix B such that A times B would be equal to B times A, which is equal to I sub n, where I sub n is the identity matrix of order n. The matrix B is called the multiplicative inverse of A. A matrix that doesn't have an inverse is called non-invertible or singular. Most of the time when we talk of inverse, we symbolize it as A with a negative 1 as an exponent. So this is the symbol that we can use for the inverse of A. So B will be the inverse of A, provided that if we multiply A to B and then B to A, it will give an identity of order n. Apart from this, you can see that the requirement is that the matrix A is n by n. What does this mean? We can see now that non-square matrices do not have inverses because the first requirement of the definition is that it's an n by n matrix, meaning it should be a square matrix. However, if we're going to go back to the definition, the matrix A, that square matrix, is invertible if B exists. If B does not exist, then the matrix, even though it's a square matrix, is singular or it does not have an inverse. So this would also mean that not all square matrices have inverses. So at the start, we're going to deal with square matrices. If we don't have a square matrix, then we cannot find its inverse. One theorem closely related to this is the uniqueness of an inverse matrix. So, if A is an invertible matrix, then its inverse is unique, denoted by A raised to negative 1, or read as the inverse of A. So this theorem is telling us that if we find the inverse of A, it is unique to that specific matrix. We cannot have a matrix with two inverses. There's only one inverse of a specific matrix. So let's have an example. Let us show B is the inverse of A, where A is equal to this matrix and B is equal to this matrix. So based on the definition, A times B should be equal to B times A, which should be equal to, in this case, I sub 2. So let's see. First, let's multiply AB, which would be negative 1, 2, negative 1, 1, multiplied to 1, negative 2, 1, negative 1. So therefore, if we're going to multiply this one, I'll have negative 1 times 1 plus 2 times 1, 2 times 1. Then I'll have negative 1 times negative 2 and 2 plus rather 2 times negative 1. Then I'm going to have negative 1 times 1 plus 1 times 1, 1 times 1. Then I'll have negative 1 times negative 2 multiplied to, added rather to 1 times negative 1. There you go. Simplifying these expressions, we're going to have, this is actually 1, this cancels out as 0, this cancels out as 0 as well, and this is 1, which is actually our identity matrix of order 2. If we can show that B times A is also equal to this, then we have shown rather that B is the inverse of A. So let's just bring that up. There you go. So BA will now be equal to 1, negative 2, 1, negative 1, multiplied to negative 1, 2, negative 1, 1. Which would mean we'll have 1 times negative 1, added to negative 2 times negative 1, and I will have here 1 times 2, added to negative 2 times 1. Then I'll have here 1 times negative 1 plus negative 1 times negative 1. Then I'll have 1 times 2 plus negative 1 times 1. There you go. Oops, sorry. Let's erase that. And let's close that matrix. Simplifying this one, we're going to have, this becomes actually 2 plus negative 1, or negative 1 plus 2, which is 1. This cancels out as 0. This becomes 0 as well. This becomes 1, which is also I sub 2. And since we have already shown that A times B is equal to B times A, which is equal to I sub 2, therefore we can say that B is actually the inverse of A.